Hi, my name is Martin Tauk. I'm a grad student at Montana State University.
And I'm Andrew Hahn, and I'm also a graduate student at Montana State University.
And this video today is about the polarization of light and the Montana High School Polarization Photo Contest. We're sponsored by NASA and the local NASA branch, Montana Space Grant Consortium, as well as SPIE and Flathead Valley Community College. So we want to start by talking about why we're here. And the big reason is to introduce you to the property of light called polarization. You've probably heard of polarization in the colloquial sense, and we're here to kind of explain to you exactly what that means. And then we're here to talk about examples of polarization in nature. And so you can see we have a picture of a rainbow, and on one side a polarizer can enhance the rainbow, and on the other side it does the opposite. And so we're going to get to the bottom of why this happens. And finally, we're here to show you how to use polarization to take amazing photos for our photo contest. And we'll talk more about the photo contest and all that in a little bit, but kind of keep that in mind as we go throughout this video.
So first, before we can talk about polarization, we want to talk a little bit about light, about what light is. And light is a propagating electromagnetic wave. So you can imagine a wave in the screen moving from the left to the right. You can think of a water wave moving to the left to the right, and the wave part is the displacement of the water as it goes up and down as the wave propagates from left to right. In this case, these vectors kind of go up and down. Instead of the surface of the water, it's the vectors that move up and down. And the electric field is that vector. So as the light propagates, the electromagnetic field oscillates up and down or side to side, and it's that orientation of the electric field that we call the polarization.
So you can imagine if we took this wave that we were just looking at and were to orient it a little differently and then look right into it, we'd see that those electric fields are moving up and down or in the vertical direction. So as Andrew just said, this is the polarization direction, and in this case it's vertical. But take that same wave and just rotate it 90 degrees, and now if we look into it, we'll notice that it's oscillating from left to right or in the horizontal direction. So in this case, we call this horizontal polarization. So imagine we have this vertical and horizontal polarization state, and we combine them together. So we do some vector algebra and take some component of y and add to that some component of x and draw our resultant, go from tip to tail, and we'll get our resultant polarization. So if we have equal parts x and y, we'll find that that polarization state is 45 degrees linearly polarized. And you can just as easily imagine reducing the amount of x or the amount of y, but in this case we've reduced the amount of x polarization in this wave, and the resultant is now going to be at a different angle, in this case 20 degrees. So you can imagine varying the magnitudes of the vertical and horizontal polarization, we can create any polarization state between 0 and 360 degrees.
Here is an animation of a 45-degree polarized light, and we actually have the vertical components and the horizontal components in there. And an important property that you can see is that the electric field of both the vertical and horizontal components are at a peak and a zero and a trough all at the same time. And that's a property of linear polarized light.
So how can we tell if light is polarized? Our eyes can't detect polarization of light, so we need some kind of method to determine if light is polarized and in which direction it's polarized. And so this may sound kind of circular, but to see polarized light, you need to use a device called a polarizing filter, or we call it a polarizer. And so you put this polarizer in between your eye and the light, and as you rotate it, if some of the light gets blocked out, you know that the light that was blocked out was polarized. And that's how you tell if some light's polarized. That's how we do it.
So we talked about how you can see linearly polarized light, but how does it even get started to begin with? Well, how is it even created? Well, some light can start polarized, like in some or most lasers. light can actually start polarized. But just like you can use the polarizer to see polarized light, any light coming through the polarizer is now linearly polarized. So that's another way that that you can create linearly polarized light. Another way you can get it is reflection from a smooth surface at a certain angle, usually a almost glancing angle. You can get off a smooth surface, like a polished wood surface or a plastic surface or some sort of, or on the road. You can get this. You can see in this diagram here. You can see that the horizontal component is the only one left over after it was reflected off the smooth surface, and that's something that we could see by taking a polarizer and rotating it appropriately and blocking it out, so we can actually see that polarizing effect. And here, it's important to note that the reflection from the tree that's out of the frame, but it's reflecting off the windshield and hitting the camera, when we put the polarizer in front of the camera and rotate it the right way, you actually see that this light is blocked completely, which means that the light reflecting off the windshield became polarized by reflecting off the windshield. But the light passing through the glass does not get polarized. That's why the person inside the car is still visible, and even more visible, actually. And another way that light can get linearly polarized is by scattering off particles of air in the atmosphere. So in this diagram, you can see unpolarized light or randomly polarized light coming and bouncing off or scattering off this molecule in the atmosphere. And depending on the angle that you're at, if there's a typical photographer down there in the bottom, you're going to see some horizontally polarized light. But if you imagine you're in a plane at a different angle, you could see some vertically polarized light. And you get the most polarization when the angle from the sun to you from that scattered particle is 90 degrees. And you see you can get partially polarized light when the angle is less than 90 degrees. And this is the result of actually light scattering off molecules in the atmosphere. On the left, you have this picture of this landscape with no filter in front of the camera, and then we put the polarizing filter or polarizer in front of the camera, and you can actually see that there's this dark band in the sky, and that is where the molecules in the sky are at the correct angle between you and the sun to create this maximum polarizing effect. And the result is you get just a much nicer picture where the mountains in the background are much more defined.
Okay, so what we're going to start with is a couple linear polarizers. So now that we've talked about linear polarization, we're going to see a few experiments and demonstrations. So to start, we're just going to take two linear polarizers that are just like this, and this one's loose and free to rotate, and the one down here is attached to this mount. And as I rotate this around, we see that the amount of intensity in that that's coming through doesn't change. And that's because our source here, this monitor that we've deconstructed, is a source of unpolarized light. And so when we take that unpolarized light and send it through one linear polarizer, no matter how we rotate that polarizer, the intensity of light coming through doesn't change as a function of angle. However, if we take two polarizers, so here's another polarizer just like the one on there, and if we take this and we put it into our setup here, like this, we've oriented these polarizers so that they're both vertical. And as I rotate this one, the top polarizer, 90 degrees, we start to see that light diminish drastically. And as I rotate it back out, we get light through again. So what I've done is I've oriented them both vertical, and as I rotate the top one, I'm rotating it into a horizontal state. And since horizontal is perpendicular to vertical, we've now crossed our polarizers and no light can come through because those electric fields are oscillating in such ways that one goes through the first one but not through the second one. And so we can do a lot of cool things with one polarizer, but we can do a lot of different things with two polarizers, like we've shown here. And we can put things in between here. That's why it's set up this way with a space. So for example, we have this third polarizer, and just like all the other ones, as I rotate it, it doesn't change. But I can take it and I can put it in between these cross polarizers. And as I rotate it around, you can see that the arrows on there indicating the direction of polarization. So as I rotate it, Here we're oriented in line with the polarizer, and here we're oriented 45 degrees to that polarizer. And you can see that when I orient it like that, we get a lot of light coming back through. As I rotate it, we get more, and then less again. And then here we're at 45, here we're at 0 or 90, at 45, and so on and so forth. And so what's going on here, if you think back to some of the images we were showing you earlier, we have x and y components for any vector of light. We can break that down into x components and y components. And so when that light comes through the vertical polarizer, let's say where it's all in y, so we have all y light, but then we send it through a polarizer that's oriented at 45 degrees. Now we have half the light in y and the other half in x. So we've gone from everything in y to half y, half x. And what we do is when we go through the third polarizer, or the crossed polarizer up here, there's x and y components, so now some of that x light is coming out. So we came in with y, turned it into x and y, and then we let the x light out. And that's what's going on in this setup here. So now that we've shown you a few photos and just defined polarization and shown you examples of how light gets polarized and things that have to do with that, you're probably wondering, how do you take these photos? How do I as a student go out and do this? And the way you do it is you take a camera and you take a polarizer, which we will supply to you, and you put the polarizer in between you, or the camera rather, and the scene, and you rotate it. So in this case, this is a hallway where we work, and Andrew's held his glasses up vertically and then horizontally, and you can see that the brightness from the reflections of the light on the ground are dimmer in the horizontal case than the vertical case. And so that's enough to take a picture that shows polarization. And I should mention that every photo in this presentation was taken by somebody here at MSU or at Flathead Valley Community College. And so if you see something you like or you think is pretty cool, you can go out and do it with this kind of method. And you'll notice in the top photo, the top scenario, the guy's holding the polarizer pretty far from the camera, and he gets the rim of the glasses in there, which we've just shown to kind of illustrate how you need to rotate it, how you need to rotate the polarizer. But if you look at the bottom section, the polarizer is much closer to the camera, which is what you typically want to do, and then you get rid of the rims and you just get the effect of the polarizer in your shot.
So here's one example photo, or two photos rather, one with no polarizer and one with a polarizer. And the main thing that you can see is that light coming from just the blue sky in the background is very polarized. So you get this reduction in intensity coming from the sky. So the result is a much darker sky, as opposed to the clouds are much clearer, because light scattering off clouds does not get polarized. It actually gets randomly polarized. So it's not affected by the orientation of the polarizer.
And in this case, we have a picture of a lake. This is the shore of a lake. And on the left side, there is no polarizer, and you get this glare off the water. So remember, reflections off of smooth surfaces at glancing angles, that causes the light being reflected to become polarized. And so you see on the left, with no polarizer, there's a big reflection, but on the right, once we put the polarizer in there at the right orientation, we've blocked out that polarized light, which is reflecting off the top of the water, so we can see down into the water, and we see the shore, we see the lake shore with the rocks and sand and everything. Here's another example photo of a hazy day. I think this is near Flathead Valley, and you see that on the left with no polarizer, it's all kind of washed out, but on the right, it's pretty well defined. And this is similar to the scattering in the atmosphere scenarios, right? You can imagine a particle in between the photographer and the mountain, and the sun being right overhead. So as that beam of light comes down and scatters off that particle, the angle between us and the sun, with reference to that particle, is 90 degrees. And so that light is very polarized. So if you block it out with a polarizer, you reduce all those scatters, the reflections off those scatters, and the photo becomes much clearer.
So now we're going to talk about how an LCD works, and what an LCD is: a liquid crystal display, like on your phones or on most TVs now, or most computer screens now, if not all computer screens now. So how they work is you have unpolarized light or randomly polarized light coming through an initial linear polarizer. So now the light has been polarized. And now we have this other device called a wave plate, or this is what the liquid crystal is. And this is a device where if we change the voltage that we apply to this liquid crystal, we can actually rotate that polarization state. So instead of coming in horizontal, like you can see there, it would actually get rotated a little bit. So if it gets rotated a little bit, if it didn't get rotated at all, it wouldn't come through that cross polarizer, that second polarizer, because if all the light's vertical from the first one, it wouldn't come through the second one, because that's only letting vertical through, and so no horizontal would even be there. But if we rotate it by applying the proper voltage, now we can get some light coming through that cross polarizer, and that's the idea of a liquid crystal display. Is you can imagine things being on where there's a voltage rotating it, then you get light coming through, and if it's off, there's no voltage, and you're not getting any light coming through.
So now that we've shown you how to take photos with just a polarizer and block some of that stuff out and then enhance the photo in some way, you can go out there and you can take cool pictures and submit them to this photo contest. But what we want to show you now is something called polarimetry, which is applying a bit of math and science to these polarization photos. And there's hundreds of applications for polarimetry. One of the most common ones is detecting man-made objects in a region, because man-made objects are typically more polarized than the natural objects. And so here we have a picture of a hallway, and it was just taken with a camera on a tripod and a polarizer right in front of it. And what we do is we take that polarizer and we rotate it in 4 different orientations. So here there's 4 pictures on the left. The first one has the polarizer oriented to 90 degrees. Then if we go in a clockwise orientation, the next one's oriented at 45, 135, and 0 degrees. And you see all these pictures are just a little bit different. The biggest difference is between the 0 degree and the 90 degree. So if we take these photos and do some math on them, and the math is described in these equations here, we can get what's called a degree of linear polarization photo. So now, instead of looking at how bright something is, we're looking at how linearly polarized something is. So blue things aren't very polarized at all, and red things are extremely polarized. So if you look at the I0 degree image in the bottom left-hand corner, you'll see that the light from the light reflecting off of the floor is pretty dim in that near reflection. And so it's really bright in the image right above it, so that suggests that that light is very polarized. And if we go over here to the blue and red degree of linear polarization picture, we see that, yeah, that's white. And if we look at our scale, white's about 0.5, so that's about 0.5 polarized, which is pretty polarized. But if we look like around the lights, the edges of the lights, those are red, and some of the corners are red. So those things are really polarized, probably because you're sweeping through a lot of angles, and at the right glancing angle, you're getting a lot of polarization. So this is a cool thing we can do. And we have some examples besides this hallway, which, although it's a very cool picture, it's a picture of a hallway, which is kind of boring. So here's a much more interesting one. This is in North Dakota, and this picture shows how you get polarization from scattering in the atmosphere, right? Here's that band we saw earlier, where there's a part of the sky that's very polarized, this kind of reddish part in the middle, and as you move away from that, the polarization goes down. But we also see that the ground and the trees and the clouds are not very polarized. Those are all close to 0 degree of linear polarization, except for a few kind of spots on the hill, and there's a couple clouds that are really polarized, it appears. But what we have to remember is that this is a combination of 3 or 4 pictures, and so as you take time to take pictures, the clouds might move a little bit, or the wind blows a little and moves some of these pieces around. And so when you combine all those photos, they don't all line up quite right if something's moving, and that makes it look like something's polarized. So it's what we call an artifact, and you have to be weary of it. You have to know about it so you don't accidentally think something's polarized when it's just an artifact due to motion between photos.
So to talk more about these polarimetry photos, just to reiterate, normal photos show the intensity of the light. So brightness in the photo corresponds to intensity. It corresponds to how much light is hitting your camera or hitting the sensor on your camera. In a polarimeter, brightness in the photo, or before it was redness, but this one's actually a grayscale, so it's actually white areas here have high polarization. So brightness here corresponds to polarization, and darkness corresponds to things that aren't very polarized at all. So we call that, again, the degree of linear polarization, or how much linear polarization is in your photo. So some things to point out here. On the left, on the top, you can see this truck here is just sort of like, you can't even see it that well, but you can imagine that there's a truck there and it's dark, probably dark colored. So you can't really see it that well in the regular intensity photo, but as soon as you go down to the DOLP photo, you can see this thing is really bright, which means it's reflecting a lot of polarized light. So this reflects actually one of the uses, is you can actually see these man-made smooth objects when you use polarimetry. Another thing here is you can see up on these mountains here, on the top it's really bright, so there's a lot of light coming from these snowy mountains up there. But as you look in the DOLP image, it's really dark, and the reason for that is the surface of the snow is not very smooth at all. There's all these little snow crystals, and so it's pretty rough, so it reflects all in random directions. So the light that's reflected is not polarizing at all. It's actually very depolarizing, or randomly polarizing. And this shows one of the best uses for polarimetry, especially in the military, is on the top right. You can't even see anything is there. Something in the trees there, so you wouldn't even see it. If we were just looking at the intensity, it would not even draw your attention. But when you look at the DOLP image, there's a very bright thing there, which means that there's something very polarizing in there. So it's probably a car or some other smooth surface. So this again shows why the military especially is very interested in things like degree of linear polarization, because they can see man-made things very easily. So here's another example of polarization, where we have an intensity photo on the left and the DOLP polarimetry photo on the right. So we want you guys to do is to identify things that are polarized or things that aren't very polarized, and go ahead and put them in the comments. And any questions you have about, maybe you see something that you think is polarized and I'm not sure why it should be, or the opposite, you think something's smooth but it's not being very polarizing. Like, if you have any questions, go ahead and ask them in the comments and we'll try to respond.
So we said this is a photo contest, and so we've got a few guidelines to keep things fair. You have to take interesting photos using or showing polarized light. You have to write an explanation of the science behind the photo. And when we judge these photos at Montana State University and Flathead Valley Community College, we're going to judge 50% on the photo and 50% on the explanation. So you need to be writing good explanations and taking good photos. One or the other won't outweigh the opposite. Photos are going to be judged at Montana State University by a panel of experts. And the contest is open now until the beginning of March 1st. So you have a number of months to kind of decide what you want to do and go out there and take those photos. The winners will be announced in mid-March, and we've got a few rules to go along with these guidelines. Photos must be taken by students. Any camera can be used, so if you've got a cell phone or you have a fancy DSLR type camera, go ahead and use that. And just like any camera can be used, any filter or polarizing optic can be used. We'll give you guys basic linear polarizers if you request them. We have those. But if you have a nice linear polarizer or circular polarizer or some kind of cool filter at home, go ahead and use it. There's a maximum of 2 entries per student, and these entries must be distinct, meaning you can't submit 2 really similar photos. They gotta have something different to show in each one. The photos must be accompanied by a single paragraph which explains the photo. That is, how was the photo taken? Why is polarization important in the photo? What can be learned from the photo? And finally, photos entered into the contest must be accompanied by a signed letter from your teacher. We just need some kind of acknowledgement that you did indeed do this and the teacher's on board and everything's cool. So we got some prizes prepared for you. The first ones we want to talk about are the honorable mentions. So a few students who have shown exceptional work in their photograph and explanation will win a visit to the optics research labs at Montana State University in Bozeman. This will include lab tours and campus visits and some fun learning activities that we've got planned. This will happen on April 7th, and the visitors also invited to participate in the Montana Space Grant Consortium Annual Symposium, as well as Astronomy and Aerospace Day, which goes on at the Museum of the Rockies, which is a great museum if you've never been there. And that's going to happen around the same time, April 8th and 9th. So you come down for that whole weekend, and there's a lot of cool stuff to do. And as far as the grand prize goes, last year we sent a student to NASA Kennedy Space Center in Florida, and I think they got to watch some kind of launch and go visit all of these cool rockets and space shuttles and a bunch of crazy stuff down there. This year, we got a little bit different thing in mind, and that's got to do with the solar eclipse happening in this summer. And so we've got a team that's ready to kind of chase the eclipse and do a bunch of cool science experiments while the eclipse goes on, because like insects come out because they think it's day, or nocturnal animals might have some weird effects. What happens to the polarization of the sky during this? All sorts of cool questions. And so we're going to be kind of driving around to an area where we can view the eclipse, and the grand prize winner will get to accompany this chase team on this eclipse, and basically just kind of get to see what it's like to be a researcher in a very, very cool time during a solar eclipse. So we're really excited about that. So to finish off, we've just got a picture here that we took in our lab, and this is a picture of, well, we kind of wanted to keep it a bit of a mystery and let you comment on what you think it is below. I also wanted to say that this is one of a series of videos. This is video number 1 out of 5, where we've talked about polarization and introduced you to the whole photo contest. But we've got 2 other videos that talk about different types of polarization. There's this crazy thing called circular polarization, and it's similar to linear polarization, which is what we talked about here, but there's a lot of other weird things and a lot of super cool things and crazy things that happen in nature with it. And we talk about that in another video. And we also have a video that shows a couple demonstrations on how you can see polarized light. We've got a polarization demonstration set up, so we kind of go through that. And then we also have 2 videos that show the basic concepts on how to take a photo using polarization. So when you're ready to go out there and take a picture and you're like, oh wait, how do I do this? You can watch that video, and it takes you step by step through that process, as well as how to use circular polarization. So there's a whole nother video that shows you how to take photos that show some kind of circular polarization effect. So look out for those. Again, if you have any comments or questions, or you didn't understand something, or thought something should be one way and it was another way, go ahead and post it down in the comments below, and we'd be happy to get back to you. So thanks for listening.